But when a subject bored him, then, you know, he didn't pay any attention at all. And on the right of the screen, you can see the results of Einstein's exit exam from his secondary school, the equivalent of high school. By the time Einstein graduated from high school, his father, in pursuit of his business interests, had moved the family to Switzerland. So this is a school in Aargau in Switzerland. And you can see the results of his exams. It's graded on a scale from 1 to 6, with 6 being the highest. And unfortunately, I couldn't get an ultra high resolution image of Einstein's exam results, but I'll just read you the subjects in which he got a 6. So let's see, history, he gets a 6, algebra, geometry, descriptive geometry, and physics. So mathematical and physical subjects, he gets a high score on. And also, oh yeah, history. He's good at telling stories. He's good at making sense out of a seemingly confused situation. His lowest score, a mere 3, passing but kind of borderline, is in French. I was very pleased when I learned this. Hey, now I have something in common with Albert Einstein. We both had mediocre grades in high school French. Well, despite his lack of facility in parlez-vousing Francais, Einstein was admitted to the Swiss Federal Polytechnic Institute, usually known by its German initials ETH. ETH was at the time and is still really the very best science and technology school in Switzerland. You can think of it as the Swiss equivalent of Caltech or MIT, really good school. Einstein did well at his studies. He graduated in the year 1900. He applied to become a graduate student at ETH, but his application was turned down. Now, in later years, Einstein always stated that it was because one of his professors really, really hated him. So he was sabotaged in his desire to go on to graduate school immediately after his undergraduate career. However, he did eventually end up with a job at the Swiss Patent Office. Again, an urban legend, Einstein's job at the Patent Office is often referred to as being a patent clerk, which gives a very misleading impression. It implies that his job was just reading papers and stamping them and filing them. But in fact, a patent examiner had a more serious job. They were supposed to not merely read through the patents and try to remember whether a similar patent had been filed, but they actually had to evaluate it. Does this gizmo actually do what it says it does? So Einstein was able to use his newly gained knowledge of Newtonian physics to apply to real-world situations. Now, although his job at the patent office was not merely menial work, he had a lot of time to think. And he thought a lot about the old-fashioned Newtonian physics that he had learned at ETH. And he started thinking of ways in which physics could be improved. And by 1905, Einstein, in what's sometimes called his annus mirabilis, his miraculous year, came up with his theory of special relativity. The image at upper right, that's Albert Einstein around the year 1905. He looks like Albert Einstein, but with black hair still. And the paper that he published in that year, and particularly in June of 1905, well, I'm showing the very beginning of the paper to you. Its title, translated into English, is On the Electrodynamics of Moving Bodies. Yeah, it's a head scratcher. Doesn't sound anything like relativity. But special relativity, it's all about moving bodies, and especially how they move when they approach the speed of light as seen by you. And electrodynamics, well, that's the field of physics that deals with changing electric and magnetic fields and the production of light. So the title seems a little odd, but it's telling us, oh, special relativity, it's all about moving objects, especially objects that move very rapidly, and it's about light. Now, the theory that Einstein published in 1905, he's still at the patent office, is called special relativity. What's so special about special relativity? Well, special relativity deals with a very special case. It deals with the special case in which there is no gravity. So if you've read anything about special relativity, it always uses examples like, well, two spaceships are moving past each other at a constant speed. Constant speed. Newton would say, oh, constant speed, that means there's no forces working to accelerate them. And in particular, there's no force of gravity. So Einstein, by confining himself to this special case in which things move in straight lines at constant speed, is forced to avert his eyes from the horrors of dealing with gravity. This leads to a problem, a really big elephant in the room problem. It's a neon elephant glowing in the dark because, let's face it, gravity exists. We don't have to worry about our parents forgetting to pay the gravity bill because gravity is always there. And in particular, astronomers are always aware that gravity is there. You look at planets in the solar system, you look at stars within galaxies, guess what? They're not moving in straight lines at a constant speed. They're moving along curved orbits because of gravity. So Einstein was aware that he had ignored the elephant in the room, and he spent 10 whole years, an entire decade, trying to incorporate gravity into his earlier theory, and thus making a theory of general relativity, dealing with a general case in which, yeah, we acknowledge gravity exists. And famously, Einstein came up with these really, really novel ideas in which he says, oh, planets move along elliptical orbits at changing speeds because, not because there's a force of gravity working on them, but because gravity is the warping or distortion or curvature of space and also of time. So Einstein says, well, the Earth is trying to go in as straight a line as possible, but because space-time itself is curved or warped, it is of necessity moving along a curved line. This was an amazingly novel idea. For over 2 centuries, people had embraced the idea of Newton that gravity is a force because Newton's ideas about gravity work very well in most cases. However, Einstein says doesn't work quite well enough. In particular, you look up Newton's law of gravity and you see, oh, Newton says the force of gravity depends upon the distance between 2 massive objects. The distance, the unique distance between 2 objects. But Einstein realized in developing special relativity that there is no one unique distance between 2 objects. The distance depends upon how rapidly an observer is moving relative to the 2 objects. So he's had to scrap everything, start from scratch, and finally, after more than 10 years, from June 1905 to November 15th, Einstein has been working away on a way of describing gravity in terms of a curved 4-dimensional space-time. This was not an easy task. Okay, understatement. This was a horrendously horrible task. And you can see in the upper right, the image of Einstein in 1915. His hair is disheveled, he's been pulling at it, and it's starting to feel a little bit gray. So the paper he published in 1915, entitled in English, The Field Equation of Gravitation, tells you the field equation. That's simply the mathematical relation that tells you how space and time are warped in the vicinity of an object that has mass. or equivalently, has energy, since energy equals mass times the square of the speed of light. Now, another understatement. The field equation of gravitation that Einstein published in 1915 is very complicated. And brace yourselves. Every scientific talk is permitted to contain one equation. Here's the equation, okay? Oh, there it is, Einstein's 1915 field equation. Actually, it doesn't look so horrible written down, but that's because it's in very compact notation. So I'll just point out a few things. The capital letter G, that's the gravitational constant. This is a leftover from Newton's law of gravity. So in Newton's viewpoint, big G is what tells you if you have a 1 kilogram mass over here and a 1 kilogram mass over there, and they're 1 meter apart, what's the force between them? So the gravitational constant is a constant of nature. It is what it is. In the bottom, that lowercase c, that's the speed of light. To a physicist, lowercase c is always the speed of light. If you try as a physicist to use a little c, meaning anything other than the speed of light, the physics police show up and take away your physics license. So when you see a c, a lowercase c in a physics equation, you can safely assume it means the speed of light. But what about those letters with the Greek subscripts? How about T sub mu nu on the right? Well, T sub mu nu is actually, it's a little trick here, it's a 4x4 matrix. It has 16 entries, and it contains information about the mass energy content of the universe. And it describes what the mass energy content is everywhere in space and also every when in time. On the left, there's another 4x4 matrix, G sub mu nu. This contains all the information about the curvature of space-time. So what this equation is saying, in very general terms, is that if you know the content of the universe, if you know its mass and or its energy, then you can compute what the curvature, what the warping of space and of time is. Or vice versa. If you can somehow measure the curvature of space-time, you can say, aha, I know how much mass and energy there is at that point. So looks simple, but remember those little Greek subscripts? That actually means it's 16 separate equations. Admittedly, there are symmetries involved that reduce it to 10 equations, but there are 10 second-order nonlinear differential equations. Very difficult to solve. Oh, and you have to solve these 10 difficult equations everywhere in a 4-dimensional space-time. Whenever I teach a class about general relativity, I use as my mascot a Shar-Pei dog. Shar-Pei dogs, really, really cute, but that's because they have this baggy, curved, warped skin. And imagine you had a theory of dogs that required you to describe the curvature of the Shar-Pei dog's skin everywhere over its entire body. And oh, by the way, the Shar-Pei is about to get up and jog down the street, so you have to do it as a function of time as well. This is what Einstein was trying to do, except not on the 2-dimensional surface of a dog, but in a 3-dimensional universe, and a universe that is, spoiler alert, a lot bigger than a dog. Very, very, very difficult equation to solve. In fact, when Einstein published his equation in 1915, he didn't have any solutions for it. A solution was soon found by Carl Schwarzschild, who found the famous Schwarzschild solution for curvature of space-time near a black hole. But again, that was a very, very simplified case. You have a single point of mass. What's the curvature around it? Einstein, knowing from Schwarzschild's result that solutions to this equation did exist, tried to find another solution to his field equation. And rather hubristically, rather dauntingly ambitiously, he tried to apply his field equation to the entire freaking universe. Now I said, this is hard. However, in February 1917, he submitted a paper, Cosmological Considerations in the General Theory of Relativity. How did he manage to find a solution for the very, very complicated field equations that covered the entire universe? Well, he did it by ruthless simplification. First of all, he assumed that the universe, which of course is full of knots of dense matter, stars and planets and people and black holes and what have you, Einstein said, oh, I'm just going to take the universe and smooth it out. I'm just going to take all the mass and energy in the universe and spread it out absolutely uniformly. So assuming that the universe is a perfectly uniform density was a gross oversimplification, of course, but it was the only way he could find a solution. Einstein also assumed that the universe is static. That's nothing is moving in it. And in particular, that the universe is not expanding. In the year 2020, of course, we know the universe is expanding. We learned it in school. The Big Bang Theory has even become the sitcom. It's a commonplace today. But in 1917, Einstein just automatically, without even thinking about it, assumed that the universe is not expanding. So why did Einstein assume a static universe? Why was this just so immediately, obviously apparent to him? Well, at the time, 1917, there was no real observational data to indicate the universe is expanding. For that matter, it wasn't even obvious that galaxies other than our own Milky Way galaxy existed. Now, it is true that people knew that the Andromeda Nebula, for instance, existed. Here's a beautiful picture taken as early as 1888 of the Andromeda Nebula. Now, when we today look at the Andromeda Nebula, we say, oh, of course, it's a spiral galaxy, very similar to our own, but no, this is the benefit of hindsight. There was much debate at the time over whether the Andromeda Galaxy was a big galaxy like our own, or if it was just a tiny little satellite of our own great big Milky Way galaxy, the only real galaxy in the universe. So Einstein didn't know whether galaxies other than the Milky Way galaxy existed, and it was obvious that the Milky Way is not expanding. By 1917, astronomers had measured the Doppler shift of relatively bright nearby stars within the Milky Way galaxy. And some of them are moving towards us, some of them are moving away from us, but there was no overall uniform expansion, or for that matter, overall uniform contraction of the Milky Way. So in the absence of observational evidence that the universe is expanding, Einstein just said, oh, okay, the universe is static. It's not expanding, it's not contracting. This posed a problem because using the field equation that he first published in November of 1915, the equation on the top, Einstein wasn't able to find a static solution. What he did in 1917 was basically to add a fudge factor. So remember, in the field equation on the left, you have this 4x4 matrix that tells you the curvature of space-time, everywhere in space and every when in time. On the right, you have another 4x4 matrix that tells you what the density of mass and energy is, everywhere in space and every when in time. In order to keep the universe from expanding or collapsing, Einstein had to introduce another term. And this term involves the Greek letter lambda. Lambda is just the mathematical symbol. When writing, Einstein called it the cosmological constant. No one seems to be quite sure why he picked the letter lambda. since in German, cosmological and constant both start with a K. That would be a kappa. It's been suggested that lambda stands for levity in opposition to gravity, because in Einstein's static model of the universe, the one that he published in February 1917, there's an attractive force of gravity tending to pull matter together. All the stars within our Milky Way galaxy are being pulled together. And he needed a, again, I'm using Newtonian language here, he needed a repulsive force, something to oppose gravity, something that levitates the universe and pushes it apart. And so lambda, the cosmological constant, he realized, once I stick it into the equation, bing, the universe no longer has this tendency to collapse in on itself under its own gravity. Another interesting side effect that Einstein found, once he fiddled with the equations, putting in this fudge factor, lambda, the cosmological constant, the existence of lambda causes the curvature of the universe to be a positively curved space. It's no longer Euclidean or flat. It's now curved. And a very quick coverage of Euclidean language. Something is flat or not curved when it follows Euclid's laws of geometry. So a two-dimensional flat space would just be a plane. You can also have something negatively curved. That's where you take the plane and you assume it's something stretchy like rubber, and you curve it so that this is kind of the shape of a potato chip or a saddle is the usual analogy used. However, Einstein's model universe with a cosmological constant lambda added has positive curvature. And the two-dimensional space that has positive curvature is the surface of a sphere. So Einstein says, okay, in order to keep the universe from collapsing, I have to put in this fudge factor, lambda. Oh, let's call it the cosmological constant. That sounds very impressive. But putting in lambda to keep the universe from collapsing also warps the entire universe so that it's positively curved. Notice that on a positively curved two-dimensional surface, like say the surface of a spherical planet, you can circumnavigate the positively curved space, like Magellan's expedition going around the Earth. Similarly, in a positively curved universe, you can circumnavigate the universe and come back to where you began. Now, using Einstein's numbers for the density of the universe, he figured it would take about 100 million years to circumnavigate the universe. So not a very practical thing to do, but in theory, if Einstein were correct, you could circumnavigate the universe. Just go in as straight a line as possible, and you would end up back where you began. Now, Einstein published his results, so he didn't hide it away in a drawer someplace. At some level, he was rather proud of his new cosmological model. However, he kind of had this love-hates relationship with his new cosmological constant lambda. So we can reconstruct what Einstein was thinking at the time from letters to his colleagues. How did Einstein view lambda? Well, from a pure physics viewpoint, he said, oh, it's another constant of nature, like the gravitational constant, big G, or the speed of light, little c. Lambda is a constant that sets that very special, unique density of mass and energy, which the universe is static. So, okay, if he puts on his physics hat, he says lambda is a new constant of nature. However, Einstein, when writing down a new theory, was always very, very concerned with aesthetics, with the beauty of the theory. He always wanted his theory to be as beautiful as possible. And like most physicists and mathematicians, Einstein's view of beauty was very minimalist. Less is more, as Mies van der Rohe would say. And so the fact that he had to add this fudge factor, the fact that he had to do this kludge to his beautiful equations by adding lambda, he said a couple of years later, it was gravely detrimental to the beauty of the theory. He didn't like it because it was ugly. It offended his sense of aesthetics. However, regarding it technically, he found that the introduction of lambda was a big relief because he had been wrestling with the boundary conditions in the problem. Physicists often worry a lot about boundary conditions. For instance, if I wanted to calculate the temperature in the room where I'm sitting in, I would have to worry about the boundaries. Is the window and door open? Can I get a breeze of cool air going through? Is the floor hot because I'm right over the kitchen? That will make the air near the ground hotter than near the ceiling. So boundary conditions are very important in physical problems. And Einstein had been wrestling with these horrible boundary problems. And finally, in a positively curved universe, there is no boundary. Just as on a spherical Earth, you can't fall off the edge because there's no edge. In a positively curved three-dimensional universe, you can't reach the boundary because there is no boundary. So Einstein had very mixed views. I mean, yay, it made his boundary problems go away. Yay, it enabled the universe to be static, but it just nagged at him that it was so ugly. Nevertheless, from 1917 onward, people said, hey, we have a solution for Einstein's new field equation that describes the universe on large scales, and the universe is static. Okay, seems like a solved problem, right? It has all the authority of Einstein behind it. And from 1919 onward, when gravitational lensing predicted by Einstein was famously seen during a solar eclipse, general relativity was, if you'll excuse the pun, generally accepted among physicists. So, okay, check that one off our list. General relativity provides a solution to the curvature of the universe on large scales. Well, I didn't promise you universal peace and harmony. I promised you a smackdown. And with a smackdown, of course, you need two people smacking each other. So here comes the second protagonist of our story, Alexander Alexandrovich Friedmann, born about 9 years after Einstein. Friedmann was born in St. Petersburg, Russia, and spent much of his life there. Unlike Einstein, whose father was an engineer, Friedmann was sort of born into the very rich, lively mathematical world of St. Petersburg. Friedmann's father, also named Alexander Alexandrovich Friedmann, started out as a ballet dancer and later became a composer of music for ballets. Friedmann's mother, although not a composer, was by all accounts a very accomplished musician on both the piano and the violin. Friedmann, however, didn't become a musician. He decided he wanted to become a mathematician. Okay, I don't know whether his parents would have preferred a musician, but they let him go off to St. Petersburg University. In the upper right, you can see it was, at the time, St. Petersburg Imperial University, sponsored by the Tsar. Very impressive neoclassical buildings. And Friedmann spent 4 years there in the mathematics department, graduated in 1910, and went on to do graduate work. However, as he was getting his master's degree in mathematics, he became more and more interested in applied mathematics. He wasn't so worried about this very, very abstract pure mathematics, he became intrigued with problems where you could apply mathematics to real world problems. So after he got his master's degree, he went to work as a meteorologist. Sounds a little bit mundane, but in fact, meteorology requires knowledge about fluid dynamics, how gases move. And in particular, it requires grappling with the difficult problem of turbulence in gases, turbulence in the motion of gases. Turbulence tied to chaos theory, even today, it's not a solved problem, which is why the weather forecasts more than a few days ahead, kind of a little bit iffy. Turbulent atmospheric motions, very difficult problem. So although Friedmann wanted to become an eminent meteorologist, something happened in the form of World War I. He joined up with the Imperial Russian Air Service, where he was permitted to keep working at meteorology. Especially at the beginning of World War I, aircraft were very fragile. In the lower right corner of your screen, you can see the result of an unsuccessful flight by a Russian imperial aircraft. So the Air Service was, of course, very, very interested in being able to predict weather accurately so they could ground their planes when severe weather was about to come through. In addition to doing weather forecasting for the Russian Air Service, Friedmann also did reconnaissance flights in planes. He wasn't just a desk jockey. And he also got involved in studying the aerodynamics of bombs. So Friedmann went up in a plane and, well, at the time, the biggest bombs that the Imperial Russian Air Service had a weight of 1 pood. A pood is a wonderful Imperial Russian unit, equal to about 36 pounds in modern units. So Friedmann picked it up, tossed it overboard. This is how you bomb something in World War I. So he's doing all of these things simultaneously. He's also getting involved in building new factories to build bombs. He's doing a lot of different things. The Treaty of Brest-Litovsk ended Russia's involvement in World War I, but of course that led to the Russian Civil War between the Bolsheviks and the anti-Bolshevik forces. During the Russian Civil War, Friedmann's life, like that of most Russians, was extremely turbulent. He went out to Siberia to a newly formed university. He returned to St. Petersburg, and the return to St. Petersburg was really a homecoming for Friedmann. He returned to the mathematics departments at St. Petersburg University, now called Petrograd University, as a professor. So on the right, a group of mathematicians from St. Petersburg University. I've circled in Friedmann so you can see him. So this was a photograph, I'm told, from before World War I rather than afterwards, but it gives you an idea of what mathematics was like in St. Petersburg at the time. Female mathematicians outnumbered, but not non-existent. And of course, at the time, getting a formal portrait taken meant you put on your best clothing, your high collars and your ties. So rather a formal setting. After the Civil War in 1920, things were still very turbulent, very difficult to get money or supplies. Students at the time in St. Petersburg talked about listening to lectures while wearing their full winter gear because there was no money to heat the buildings, and only going to lectures during the daytime because there was no money for electric lights. Friedmann, however, very hard worker, continued to work on problems about turbulence and airflow, aerodynamics, and it seemed like he was on his way to an eminent career as a meteorologist and a student of fluid dynamics. However, although initially the Soviet Union, under the rule of Lenin, You can see him here lecturing to a large crowd in Petrograd in 1920. Although initially people shunned Bolshevik Russia, by the year 1921, finally relations with Bolshevik Russia, the Soviet Union, had normalized enough that scientific papers were finally reaching Russia from Germany, their old enemy. And in particular, Friedmann was fascinated by this new idea about general relativity. So Friedmann, with another professor who had been a prisoner of war in Germany and had learned about this new general relativity idea firsthand, the two of them set up a seminar on general relativity so that they could teach each other these new ideas about general relativity. And in fact, Friedmann became so adept at coping with these complex field equations of general relativity, by June of 1922, not long after he first encountered Einstein's papers, Friedmann wrote a paper applying Einstein's field equation to the entire universe. Okay, this is just what Einstein had done. Friedmann also did the same approximation of assuming the universe is perfectly smooth, the density is the same everywhere. But Friedmann has said, yeah, I don't need this cosmological constant, lambda, boom, tosses it away. Presumably, he too thought it was ugly. He thought, I can do without this. So the paper written by Friedmann, in English translation called The Curvature of Space, was published in a German journal. At the time, Germany was still pretty much the international language of physics. So if you wanted to get noticed, you had to publish in a German language journal. And publishing in Russian just wouldn't have gotten the same audience. Friedmann's results, skipping over large quantities of math, was that a universe containing only matter, ordinary stuff, stars and planets and whatnot, can't be static. It must be either expanding or contracting. So Friedmann's saying, yeah, okay, we don't need lambda, but we must then admit that the universe is either uniformly expanding or uniformly contracting. Interestingly, although Friedmann published in German, his paper was originally written in Russian. Friedmann had a library that contained books not merely in Russian, but also German, French, English. He had a reading knowledge of all major European languages, but apparently the subtleties of what he wanted to say he couldn't handle in German. So he wrote the paper in Russian. You can see it was typed out in a Cyrillic typewriter with German names like Einstein and the name of another cosmologist, de Sitter, written in by hand. But it was then translated into German before publication. The most interesting sentence in Friedmann's paper, and now I'm translating it into English, was when he said, the world period becomes of the order of 10 billion years. The world period, that's the phrase Friedmann was using to describe the time that has elapsed since an expanding universe had started to expand. Now, in 1922, he's probably the only person in the entire planet, possibly the entire universe, who believes that the universe is expanding. Nevertheless, despite the lack of observational evidence, he's gotten a number that's really remarkably close to the modern number of 13.7 or 13.8 billion years. Okay. Ready for the smackdown? Einstein says static, Friedmann says expanding. Let the smackdown commence. Einstein, of course, kept careful track of the physics literature, especially papers relating to his baby, his theory of general relativity. In September of 1922, same year, Einstein wrote a rebuttal to Friedmann's paper, and so published under the title, Comment on A. Friedmann's paper on the curvature of space. Well, what comment does Einstein have? Well, let's look at some of the translation here. Well, what does Einstein say? In reality, it turns out that the solution given does not satisfy the field equation. Ow! Ouch, 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 ouch. In the world of physics, that's a severe smackdown. Einstein is saying, you did not solve the problem correctly. You made a mistake. And he goes on to say, the results concerning the non-stationary world, that is, the expanding universe, appear to me suspicious. I know, doesn't sound terribly rude or insulting, but in the sedate world of a physics journal, this was a real smack to the face to Friedmann. Well, what does Friedmann do? Well, things get a little complicated at this point because just after publishing his slap in the face to Friedmann, Einstein wins the Nobel Prize in Physics. If we look at his Nobel Prize certificate, it says he won the prize, quote, for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. Notice that Einstein's Nobel Prize says nothing about relativity. This is because there was still an old guard of grumpy old men physicists who refused to accept the ideas of relativity. They were still clutching desperately to Newtonian physics. However, the work that Einstein did on the photoelectric effect, kicking electrons out of atoms using photons, particles of light, was definitely in and of itself worthy of a Nobel Prize. So think of what must have been going through Friedmann's mind. First of all, Einstein says, no, you solved my field equations wrong, wrongity, wrong, wrong, wrong. And then coming on that, oh, Einstein has just won the Nobel Prize, which pretty much makes him top dog in physics. Okay, how do you respond to somebody who's just won the Nobel Prize in physics? Well, Friedmann, first of all, decides to write a letter to Einstein. So he's doing this privately. He is not, like Einstein, publishing a paper in a journal that everybody can read. He wants to approach this in a civilized, quiet manner, man to man. Moreover, the letter that he wrote was excruciatingly polite. He begins out, much esteemed professor. Now, mind you, this was a more formal age. If anybody wrote me a letter starting much esteemed professor, I'd probably die of shock, but still, he's writing about his esteem to somebody who just said, you're wrong. You made a bad mathematical mistake. The letter goes on, very carefully laying out every step in Friedmann's calculations, pointing out the total complete lack of mistakes in calculation. And Friedmann ends up his letter by saying, should you find the calculations presented in my letter correct, please be so kind as to inform the editors of the Zeitschrift für Physik, the journal in which Friedmann and Einstein had been publishing. Please inform the editors of the journal about it. Perhaps in this case, you will publish a correction. So on the one hand, he's being ridiculously over the top polite. On the other hand, he's not backing down. He says, I am right. These are my calculations. If you agree with them, perhaps you could tell the editors of the journal to publish a correction of your paper, not mine. Unfortunately, when Friedmann sent off his letter to Berlin, where Einstein had a university job, Einstein was traveling. In fact, at the time, he was in Japan, making his only visit to that country. On the left, you can see Einstein, shoes off, gamely trying to drink some sake. And in those days, when you went to Japan from Europe, it took a while. And in fact, Einstein didn't return to Berlin until March of 1923. So this is after about half a year of traveling. He has a stack of mail on his desk, I'm sure, that's several feet high. And he doesn't get back to Friedmann right away. However, by May of 1923, a couple of months after his return from Japan, Einstein writes to the editors of the Zeitschrift für Physik, and what he writes is a retraction of his rebuttal. Now, what I'm showing you on the screen now is Einstein's May 1923 paper in full. This is the entire paper right here. So if you can read German, you know exactly what Einstein said. For people like me who don't know any German at all, I've put up a translation of the 3 main sentences of the paper. It's from the standard English language translation of the works of Einstein. Einstein is fessing up. He says, in an earlier note, I exercised criticism on the mentioned paper, that is Friedmann's paper on the curvature of space. My objection, however, and this is where he admits the truth, was based on a calculation error. Oops, he's putting his hand up. The calculation error was mine, it was not Friedmann's. He says, I've been persuaded at the suggestion of Mr. Krutkoff, guided by a letter by Mr. Friedmann. Who's Mr. Krutkoff? Well, he's a colleague of Einstein's who happened, a colleague of Friedmann's at St. Petersburg, who happened to meet up with Einstein at a conference in Ryden in the Netherlands. And Krutkoff stood up for Friedmann. He sat down with Einstein and went through line by line all of Friedmann's calculations. So it was really Krutkoff shoving Friedmann's calculations under Einstein's nose that really convinced Einstein that he was wrong. And finally, Einstein says, I consider Mr. Friedmann's results correct and illuminating. So, interesting. The Smackdown ends with Einstein, the famous, world famous Albert Einstein, Nobel Prize laureate, admitting that he's wrong. Einstein made mistakes, and bless his heart, when he realized he made a mistake, he always openly admitted it. Another bit of information about what Einstein was thinking at the time came in a postcard that he wrote to a friend of his, Hermann Weyl, a very adept mathematician. It's the same month, May of 1923. He just dropped a postcard in the mail, not saying having a great time, wishing you were here, but he's saying if there is no quasi-static world, that is, if the universe is not static, if it's actually expanding, then away with the cosmological constant. Einstein still hated the cosmological constant because it was ugly. And now, by this point, he's on the verge of accepting the expanding universe. He's saying, if only there were observational evidence that the universe is expanding, then I will gladly get rid of the cosmological constant. Well, March 1929, less than 6 years later, Edwin Hubble comes up with the evidence that the universe is not static. He shows that galaxies are moving away from us with a speed proportional to their distance, just what you would expect in a universally expanding universe. So Einstein's response was, away with the cosmological constant. He was able to get rid of this ugly fudge factor, lambda. So finally, in 1929, Friedmann is fully triumphant. He's vindicated. Yes, the universe is expanding. Unfortunately, if you remember Friedmann's dates of birth and death, Friedmann didn't live long enough to see Hubble's results in 1929. It's a sad story. It starts out, however, with a heroic act on Friedmann's part. In July of 1925, Friedmann, who's still interested in turbulence and fluid dynamics, goes with his pilot, Pavel Fedoseyenko, to the base of the stratosphere. They're going up in a balloon, similar to the one you see on the right, and they set what at the time was a Soviet altitude record in a balloon of 7.4 kilometers, 24,300 feet. Pretty impressive. Very few people had been higher. And some of the people who had been higher, like George Mallory on Mount Everest, kind of died from it. However, Friedmann and Fedosienko came down safely. However, Friedmann realized it was a pretty strenuous flight. They were using artificial oxygen, didn't work too well. It was, of course, very cold up there, even by Russian standards. So Friedmann decided, it's time for a vacation. He went off for a couple of weeks with his wife in the Crimea, known as the Russian Riviera at the time, a beautiful place to spend July or August. And by all accounts, Friedmann had a wonderful time, very relaxing. However, he had to get back to work in St. Petersburg. By that time, he was the head of the Geophysical Institute there, a very important person. But on his return to St. Petersburg, the usually indefatigable Friedmann started to feel really unwell. And as he got sicker and sicker, he realized that on the train ride back from the Crimea to St. Petersburg, he had seen a fruit vendor with some beautiful looking pears. So he bought some, and he ate them without washing them first. This was a bad move because, well, he came down with, was diagnosed as typhoid fever. Typhoid fever transmitted by, it's caused by a salmonella bacterium, I believe. Really nasty stuff. Before antibiotics were in use, about 10 or 20% of all people who came down with typhoid fever died of it. Now, Friedmann was a generally healthy individual, still in his 30s, only 37 years old at the time. Maybe he would have survived if he hadn't undergone the physical strain of the balloon experiments going up to 7.4 kilometers with inadequate clothing and oxygen. Hard to tell. It was, however, a very great loss to physics at the time. However, frankly, it could have been worse because, remember, on his balloon flights, Friedmann's pilot, Pavel Fedosienko, was one of the greatest balloonists in Russia at the time. And less than a decade after Friedmann's death of disease, Fedosienko died a much more gruesome death still when his balloon plummeted to the earth from a height of 22 kilometers, 3 times the altitude of Friedmann's flights in 1925. So Friedmann knew at the time, with his record-breaking balloon flight, he was doing something hazardous. He didn't realize, however, that the hazard would come from eating a seemingly innocent pear on his way back from the balloon flight. So on the one hand, goes to show you that when you have a smackdown in physics, it's not always the Nobel Prize winner that wins. And in the end, yeah, Friedmann was justified. The universe is still expanding. It's become such a commonplace to us. The expanding universe even appears in New Yorker cartoons nowadays. However, if you want to know about Einstein, Friedmann, smackdowns, or the expanding universe, I'd love to take your questions now. Okay, there's a question in the chat. Why did Friedmann assume an expanding universe and not a contracting one? Yes, it is true that Friedmann's equations completely reversible. They describe an expanding universe, but if you run the film in reverse, they equally well describe a contracting universe. So why Friedmann assumed expansion rather than contraction was, well, I told you that physicists think of boundary conditions as being extremely important. However, initial conditions are also extremely important. So you have a boundary not merely in space, but you have a boundary in time. What are conditions like at the beginning? And so if you have an expanding universe, you could say, oh yeah, it started out very compact and dense, and something triggered an expansion. But if you have a very, very, very large universe, it's difficult to think of something that would cause it all to contract simultaneously. Now, one of the ideas that was triggered by Friedmann's publication was the idea of a universe that expanded to a maximum size, then contracted, and then bounced again in a big bounce, expanded and contracting, a sort of cyclical universe. So in that case, when the universe reaches its maximum size, it does start contracting, but it reaches maximum size because it started expanding in the past. So it was easiest conceptually to think of something expanding outward from an initial dense state rather than starting out very, very low in density and then collapsing in on itself. It is true, however, that for every expanding solution of Friedmann's equation, there's a contracting solution. Okay, another question? Was the cosmological constant term put back in to account for dark energy? That's a subject of another talk, but yeah, cosmological constant lambda, boing, reappears every now and again in the history of cosmology. And one of the possible explanations for the recent observations indicating the expansion of the universe is speeding up is saying, oh, there exists a cosmological constant, but lambda is very small. It only manifests its repulsive force after the universe has expanded for a while and has diluted the density of matter. So a cosmological constant could actually exist, but we don't know yet. This is why there are observational programs like the Dark Energy Survey to try to pin down the properties of whatever it is that's causing the expansion of the universe to speed up. The generic term is dark energy, but dark energy is just another way of saying whatever it is that causes the expansion of the universe to speed up. So a cosmological constant is one particular form of dark energy. Ooh, more expansions, more questions. Did the universe expand after the Big Bang due to explosive force, then slow? And then later there was accelerated expansion due to dark energy. Yeah, now we're getting into some interesting details of the expanding universe. Friedmann, when he wrote down his equations in 1922, assumed that the only thing in the universe was just ordinary matter, stars, planets, what have you. He stated that, oh, my equations imply the universe could have expanded from an initial dense state. He didn't speculate, however, about what that initial dense state was. Now, if you take an expanding universe according to Friedmann's equations and run it backwards, what you end up with is an infinitely dense point mass. Not very physical. So as you go backward in time in an expanding universe, you go back to times when the density of matter and of energy in the form of light was very, 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 very dense. Insert as many varies as you want. So our knowledge of physics just isn't sufficiently complete to tell us what the state of the universe was at extremely high densities. So the question of what put the bang into the Big Bang, still not answered. There's plenty of speculation. Physicists love speculating. And so after whatever it was that caused the universe to start expanding, first it was dominated by energy in the form of very high energy photons and neutrinos. Later on, after it expanded and cooled, matter, including dark matter, dominated most of the mass energy density. And looks like Recently, over the past few billion years or so, it's been dark energy, possibly a cosmological constant, that's provided the majority of the energy density of the universe.
Okay, any other questions? Good, put them in chat.
Hey,
All right. Go ahead, I'm sorry.
oh, I was just exhorting people to keep track of what's happening at Perkins, the virtual observing. And since this particular talk didn't end in a crash and burn disaster, I'm hoping there will be future Zoom New Vistas talks later this year.
Indeed, there will. Next month, Scott Gowdy is giving his talk about the Habitable Planet Observatory that's going to be launched. And that's going to be on October 8th at 8 p.m. And again, there'll be a Zoom link for it posted to our website. So watch for that. I'll also send it out to the email list. If you'd like to get on that email list, send me an email. I'll type it here real quick in the chat. And I'll add you to the email list for getting announcements for these programs. So thanks a lot. Also, for those that may have joined later, this has been recorded, and I will probably set up a special YouTube account to post this to for New Vistas Talks. So I'll send out an announcement to that once that's happened. So if you didn't get to hear the whole thing, although I did start it like 2 minutes into your talk, the recording, unfortunately, so just missed a brief little bit of the introduction. Again, we're just still trying to work out all these technical details on this. So, yeah, I'll post a link to that once it's up on YouTube. So again, thank you, Dr. Ryden. It was a good talk and appreciate it. And look forward to you folks coming and joining us again tomorrow. We got the hopefully either observing or planetarium show tomorrow. Link on our website for that Zoom link. And that's it. Thanks a lot. And let's see.